Hi there. In the research field of algorithmic fairness, people often talk about the importance of taking into account the sociotechnical context of a machine learning system. And in today's video, we're going to talk about a few reasons why context matters if we care about fairness. So without further ado, let's get started. One of the most important tasks of a data scientist is to translate a real-world problem into a machine learning task. And like any model, a machine learning model is just a simplification of reality. And to get to this simplification, a data scientist needs to decide which elements of the real world will be part of the model and which elements will be left out of scope. For example, we need to decide which data we're going to use, which algorithms we're going to consider, and what we want the output of our model to look like. Removing details to focus attention on general patterns is also known as abstraction. Abstraction is a fundamental aspect of many concepts in computer science. In machine learning, we use abstraction to compress relevant information of the real world into a clean mathematical function. Unfortunately, it's a trap. When we consider fairness of machine learning systems, it is tempting to put all of our attention on our model. But the impact of our model occurs in the real world. If we ignore some of the context, we might accidentally ignore some of the impact as well. In this video, we're going to talk about 5 traps you might fall into when abstracting away the context of your machine learning model. The framing trap. When we think about evaluating our models, we usually consider things like the model's predictive accuracy or how well it generalizes to new data. But although I depicted it here as a very nice little cloud, data doesn't just appear out of thin air. It is collected with a particular purpose in mind and within a particular context. On the output side, machine learning models are hardly ever the final step in a decision-making process. Other machine learning models may be involved, or there could be a human in the loop. We fall into the framing trap when we do not take into account all the relevant parts of the larger sociotechnical system that our machine learning model is a part of. Let's consider a resume screening model that is used as a decision support tool for recruiters. Now imagine that recruiters can use our tool to decide which people are invited for the next step in the hiring process. And in this way, they can spend a little bit less time scrolling through resumes and a little bit more time talking to people. When we think about the fairness of such a tool, we might want to consider whether it works equally well for different demographics to mitigate the risks of employment discrimination. However, the output of our model is not the output of the hiring process. And in this particular scenario, there is also the recruiter who plays their part. Different recruiters may interpret the output of the tool differently, depending on their own personal experience and also their own unconscious social biases. Before we even get to resume screening, candidates first need to apply for the job. Maybe some people didn't see the job ad. And there also may have been some potential applicants who didn't feel like they qualified for the job based on how it was described. The resume screening process is usually followed by a round of interviews. Again, unconscious biases of the interviewing committee may influence their decisions. So checking only for fairness of the outputs of a resume screening model is unlikely to prevent employment discrimination. To avoid falling into the framing trap, we need to consider that the tool is part of a larger socio-technical system involving both humans and other processes, and how this may affect any downstream harms. The portability trap. One of the great things about abstraction is that it increases the portability of a solution. And this basically means that the same code can be reused in completely different settings. For example, a deep learning algorithm that was originally developed in the medical domain may be applicable to problems in the financial domain or on social media platforms. We fall into the portability trap when we use a solution from one context and apply it in a different situation without taking into account the differences between the two contexts. A shift in domain, geographical location, time, or even the nature of the decision-making process can all impact the suitability of a model in a particular context. For example, the historical causes and characteristics of employment discrimination vary between countries. So imagine that we have optimized the model to mitigate racial employment discrimination against African Americans in the United States. When we blindly apply the same algorithm in the Netherlands, we may find that it's still unfair for Dutch people of Turkish and Moroccan descent, a group that has been historically discriminated against in the Netherlands, but not necessarily as much in the United States. But the portability trap goes beyond performance issues caused by differences in the data distribution. When we think about whether something is fair or not, context matters. Social norms are shaped over time and differ across situations and societies. So when we simply apply our favorite unfairness mitigation algorithm, slap a fairness sticker on a model, and call it a day, we are probably not mitigating any real-world harms. To avoid falling into the portability trap, we need to consider what it really means to be fair within the specific context of our application. So, unless your model is made out of plastic, recycling code might not be the right way to go. The formalism trap. In some cases, machine learning models are used to predict abstract phenomena that are hard to measure directly, such as socioeconomic status, employee quality, and risk of recidivism. In order to measure these abstract constructs, we need to make some assumptions about them. One way to do this is by using a proxy variable. A proxy variable is a variable that is not in itself relevant, but serves in place of an unobservable or immeasurable variable. For example, when we want to predict the risk that somebody will relapse into criminal behavior, we may use rearrest as a proxy variable for recidivism. Not all proxy variables measure the intended construct equally well. The extent to which a measurement corresponds to the thing that we are trying to measure is also known as construct validity. Construct validity is a very important concept in social sciences, but in data science it's usually not at the forefront of attention. However, many fairness issues actually arise due to a mismatch between what we are trying to measure and what we actually measure. For example, healthcare costs are an indicator of underlying health status, but they also reflect access to care. A recent study found that a machine learning model that predicted healthcare costs as a proxy for healthcare needs consistently underestimated the needs of African American patients, because historically this group has had reduced access to healthcare services. In policing, we may be interested in predicting crime, but we usually only have access to arrests, which can be racially biased. And in hiring, we may be interested in predicting employee quality, but only have access to historical hiring decisions, which can reflect unconscious biases of recruiters and hiring managers. To make things even more complicated, many demographic characteristics that we use to describe sensitive groups, such as race and gender, are complex social constructs that vary across cultures and over time. Fairness itself is a complex, abstract construct. There's a reason why philosophers, sociologists, and lawyers have long debated what is fair and what isn't. The quantitative metrics that machine learning researchers have proposed to measure fairness highlight some understandings of fairness, but do not capture everything. Most fairness metrics only consider the outcome of the decision-making process, and not the fairness of the decision-making process itself. By focusing only on the output of our models, we may neglect some issues with procedural fairness. Labeling a model as fair without explaining your assumptions and understanding of what fairness even means in the particular context is usually not the way to go. First of all, it increases the risks of falling into the portability trap, because you do not acknowledge that fairness is contextual. Second, ambiguity can make it very difficult for other people to assess and perhaps even contest your definition of fairness. And why should only developers decide what is fair and what isn't, when they are usually not the only people who are impacted by the system? So to avoid falling into the formalism trap, we need to make sure that the way in which we translate abstract phenomena into data and metrics reflects the context as well as our own moral values. The ripple effect trap. Deploying a machine learning model can have both intended and unintended consequences. We fall into the ripple effect trap when we fail to understand how the introduction of our model changes the larger system it is a part of. You may have heard of a saying called Goodhart's law. When a measure becomes a target, it ceases to be a good measure. This also applies for machine learning systems. When we make predictions based on patterns in the data, people may try to dissect how the system works in order to get a more favorable outcome. For example, since the introduction of YouTube's recommendation algorithm, content creators have long tried to identify ways to make sure their video gets recommended by the system. A few years ago, it became clear that click-through rate was an important factor. And then the platform was flooded by clickbait titles and misleading video thumbnails. As a reaction, YouTube increased the importance of watch time instead. Content creators responded by creating longer videos. None of these actions improved the quality of the content of the videos. And I'm sure you can think of plenty other scenarios in which the introduction of a machine learning model can cause people to try and game the system. Another way in which machine learning models can have unintended consequences is through runaway feedback loops. These loops can occur when the output of the machine learning system affects the future inputs of this system. For example, let's consider a predictive policing scenario. In this scenario, the data is always incomplete. We only know about crime that we were able to detect. If historical arrest records are biased against racial groups, we may overestimate the crime rates in these neighborhoods. And once we take the intervention step, we may allocate more police officers to those neighborhoods. And by default, this will increase the number of arrests in the neighborhood simply because there are more police officers around to catch crime. If then this new data is fed back into the model, we are likely to overestimate the crime rate even further. And over time, even small initial differences in crime rates can be amplified. Another consequence of machine learning models is that they can reinforce or even change power relationships between different people. For example, a machine learning model that is used to surveil employees reinforces the power of management over their subordinates. We fall into the ripple effect trap if we do not consider all these potential consequences of our model, including attempts of gaming the system, reinforcement feedback loops, and changing power relationships. The solutionism trap. As data scientists, we can be very excited about machine learning, and indeed, there is a lot of potential benefit. However, for some things, machine learning is just not the right tool to solve the problem. In other cases, the risks may outweigh the benefits, and just because you can, doesn't mean you should. In this video, we talked about 5 ways in which abstracting away the context of your machine learning model can be detrimental to fairness goals. The next time you define your machine learning task, I hope you first consider whether you have included all the relevant parts of the sociotechnical system in your model and your evaluation procedures, whether the requirements reflect the actual deployment context, whether the way you quantify variables and metrics makes sense, whether there are any possible unintended consequences of introducing a machine learning model in the existing system, and whether machine learning is the right tool for this problem. I hope this video was helpful to you, and if you still have any questions, feel free to put them in the comment section down below somewhere. And I hope to see you in our next video. Bye!